We're now going to learn how to classify critical or equilibrium points according to their type and stability. This is going to help us understand how solutions behave near a critical point. For example, over here on the right, we have a system of autonomous differential equations that has a critical point at the origin. Classifying this critical point is going to help us understand how solutions behave near this point. To classify a critical point, we need to rewrite the linear autonomous system in matrix form. A system that looks like this, dx dt, is equal to a function f of x and y, and dy dt is equal to a function g of x and y. Written more specifically like this, where we spell out what f and g are, looks like this when you write it in matrix form. This is just the derivative of vector x with respect to t, where vector x is our vector xy, and it's equal to a times x plus a constant vector b. I highlighted matrix A in yellow because that's what we're going to be focusing on. The eigenvalues that we'll call lambda of our matrix A are what determine the type and stability of each critical point, and they can be found from this characteristic equation that I've written right down here. This equation is lambda squared minus the trace of our matrix A, that's just where you take the main diagonal elements and you add them, times lambda plus the determinant of matrix A. And then you set all of that equal to 0. Solving this equation for lambda, the eigenvalues, tells you everything about the critical point, its type, and its stability. If the eigenvalues are real and are opposite in sign, you get a saddle point. And if they're real and both negative or both positive, you get what's called a node. If they're complex and have a real part that is not equal to 0, it can be negative or positive, you get a spiral. And then lastly, if you have an eigenvalue that is purely imaginary, that means the real part is equal to 0, you get a center. Now let's talk for a minute about stability. We'll start with the term asymptotically stable. A stable node and a spiral sink are asymptotically stable, and that means that solutions move toward the critical point. The next type of stability is called stable. A center is stable, and that means that solutions that start near the critical point remain near it. Lastly, we have unstable. There are 3 types that are unstable: a saddle point, an unstable node, and a spiral source. And unstable means that at least some solutions move away from the critical point. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.